Two of the most helpful tools for us to understand the properties of a linear transformation are to discover its kernel and its image. Each one of these is its own vector subspace of either the domain or the codomain, respectively, of a linear transformation. Let's take a look at how they work. The kernel of a linear transformation consists of all of the vectors in the domain which are getting mapped to the zero vector in the codomain. We think of the kernel of a transformation as those vectors which are getting erased, those vectors that are getting killed by a linear transformation. We think of this as the way in which a linear transformation can kind of lose some information and forget some of the structure, because it's collapsing a bunch of vectors from the domain, potentially, to the zero vector in the codomain. Let's look at this example of a linear transformation from three-dimensional space into three-dimensional space, and figure out what is the kernel of this linear transformation using its standard matrix, which we can see here. So how do we figure out how to describe the kernel, the set of all vectors in the domain of this transformation which are getting sent to the zero vector in the codomain? Well, we just have to solve this equation, t of v equals the zero vector, to figure out what vectors v are getting sent to zero. In other words, the kernel of t is nothing more than the solution set of the homogeneous equation which has this standard matrix and which has the zero vector on the right-hand side. Remember, this equation is always consistent because we know the zero vector itself in the domain is always sent to the zero vector in the codomain. What other vectors might also get sent to the zero vector can be found by solving the system. We can find the reduced row echelon form of the augmented matrix, identify the bound variables and the free variable, which in this case is z, and then rearrange the equations that we obtain so that we express the bound variables in terms of the free variable, and thereby discover a basis, in this example, the vector -2, -1, 1, for the kernel of this linear transformation. Evidently, this kernel is a one-dimensional subspace of the domain and is spanned by this vector -2, -1, 1. So in other words, this entire line in 3 dimensions, which has the direction vector -2, -1, 1, when this linear transformation does its work, every point on that line is getting smashed down to the origin in the codomain. So if the kernel gives us the picture of what all in the domain is getting erased, sent to the zero vector by a transformation, the image kind of gives us the opposite perspective. It tells us what vectors in the codomain are getting hit as the image of some vector from the domain. So the image of a linear transformation is the set of all vectors in the codomain which are equal to t of something from the domain. This is exactly the same thing when we study functions as the range of a function in a pre-calculus or a calculus class. It's a set of every value that this function realizes, and every linear transformation is a function. And so the concept of range for functions just shows up as the concept of image for a linear transformation, but they mean the same thing. What values is this function actually realizing? So in our example, I want to know what vectors in the codomain can we realize as t of something, where that something obviously came from the domain. In other words, for what b vectors, is it true that b is equal to t of x for some x taken from the domain? So how do we figure this out? Well, we can re-express this as the idea that these are going to be the b vectors in the codomain for which the system of equations tx equals b, or if you like, ax equals b, where a is the standard matrix, for which right-hand sides is this augmented matrix equation going to be a consistent augmented matrix equation? So the question of image is a question of how do we get a consistent system of equations. So to figure that out, let's imagine that I have an arbitrary b vector over here in my codomain. I place its coordinates b1, b2, b3 on the right-hand side of my augment bar, and I just do my usual thing to find the solution set of this linear system. What is going to guarantee for me that this becomes a consistent system at the end of the day? Well, if I do all the row operations with these arbitrary b1, b2, and b3 in their places, then I'm going to get some nasty expressions involving b1, b2, and b3 on the right-hand side of my augment bar. And we notice that just as in our kernel row reduction, we end up with an entire row of zeros on the left-hand side of this augment bar when we do that work. And so in order for this to be a consistent system, this expression, which is on the right-hand side of this equal sign, right, 0 equals something, we're only going to get a consistent system if this expression is equal to 0. Otherwise, we're going to get a 0 constant on the left-hand side of the corresponding equation and a non-zero constant on the right-hand side, which is a contradiction. That's what we don't want. So this system will be a consistent system, so b is going to be equal to tx for some x from the domain, exactly when this expression, negative b1 minus b2 plus b3, is equal to 0. So this is my necessary and sufficient condition for us to have a consistent system in this example. So what is that really describing? We need, in order for b to give us a consistent equation, for the x, y, and z coordinates of b to satisfy this equation. In other words, b must belong to the set of points in 3 dimensions which satisfy the equation minus x minus y plus z equals 0. In other words, that ends up being this 2-dimensional plane inside of 3 dimensions, right? So that's one way of understanding what the image of this linear transformation is. It's the plane whose equation is minus x minus y plus z equals 0. Of course, there's a better way to understand a subspace in linear algebra. Rather than writing down what we call a level set equation for it, instead, we can express it in terms of finding a basis for the image. And the quick and dirty way to find a basis for the image is just to ask yourself, well, what is going to become of the standard basis vectors for my domain? What are the images of those standard basis vectors going to be? Well, the first standard basis vector, its image under this transformation, is going to be the first column of the standard matrix, minus 1, 1, 0. The image of the second standard basis vector is going to be the second column of my matrix, 2, minus 1, 1. And the image of the third standard basis vector, 0, 0, 1, is going to be the third column of my standard matrix, 0, 1, 1. So these 3 standard basis vectors in my domain, when I apply this linear transformation to them, the images of those 3 standard basis vectors are going to be the 3 columns of the standard matrix. That is exactly what makes the standard matrix a standard matrix. But we notice when we did this reduced row echelon form that there were 2 pivot columns out of those 3 columns of my original matrix. Remember that the pivots mark which subset of my original columns form a linearly independent set. So the fact that the first 2 columns had pivots in my reduced row echelon form, but the third one did not, means that the third column is a linear combination of the first and second columns. That's true in my reduced row echelon form, and it also must be true, therefore, in my original matrix. In other words, this third column, 0, 1, 1, is already a linear combination of the first column, minus 1, 1, 0, and the second column, 2, negative 1, 1. Therefore, a basis for the image of t can consist of just the vectors minus 1, 1, 0 and 2, negative 1, 1. Because that is a linearly independent set, because those 2 vectors had pivots in their columns. And it's also going to be a spanning set for the entirety of the image. Because after all, linearity tells me that if I know where each of the 3 basis vectors from my domain land, then the set of linear combinations of those images are going to be where everything lands. In other words, once I know where these 3 vectors go, any other vector from my domain is just going to go to a linear combination of those 3 images. So these columns of our matrix form a spanning set for the image. Problem is that all 3 of them don't form a linearly independent set. So if we take just those columns that had the pivots, we will get a linearly independent spanning set, in other words, a basis. So this is most often how we describe the image of a linear transformation in linear algebra. We take the standard matrix, we find its reduced row echelon form, and the pivot columns in the original matrix form a basis for the image of t. So to wrap this up, we can also notice one more thing about a relationship between the kernel and the image. The dimension of the image of a linear transformation is just going to be the same as the number of pivot columns. After all, that's where we got our basis from. Basis was the pivot columns of the original matrix. And so the number of pivot columns in the reduced row echelon form is going to be the same as the number of vectors in my basis, and therefore it's going to be the same as the dimension of the image. We call that dimension the rank of this linear transformation. So the dimension is the number of pivot columns, the dimension of the image. But what about the kernel? What's the dimension of the kernel going to be? Well, it's going to be the same as the number of vectors which were in our basis for a solution set of the homogeneous equation. But the dimension of the solution set of an equation is going to be the same as the number of free variables that we discovered in the process of finding the same reduced row echelon form, but for the homogeneous equation where the right-hand sides were all 0. And the number of free variables is the same thing as the number of columns that did not have pivots. Therefore, the non-pivot columns are enumerating the dimension of the kernel, and the pivot columns are enumerating the dimension of the image of our linear transformation T. Therefore, they have to be related one to another. Specifically, if I add this number and that number, if I add the dimension of the kernel to the dimension of the image, I'm adding up the number of non-pivot columns and the number of pivot columns in the reduced row echelon form of my matrix. And since every column either is a pivot column or is a non-pivot column, when I add those two numbers together, they should total to the number of columns in the matrix A. And where does the number of columns in the matrix A comes from? It's exactly equal to the dimension of the domain of my linear transformation. This result is called the rank plus nullity theorem. The rank being the dimension of the image, which is the same as the number of pivot columns, the nullity being the dimension of the kernel, which is the number of non-pivot columns, and the rank added together to the nullity. In this case, the rank was 2, the nullity was 1. I add those two together, I get 3, which is the dimension of my domain, which is the same as the number of columns that were in my standard matrix. So the kernel and the image of a linear transformation tell us a lot about the algebraic properties of that transformation. And this video gave us an overview about how to find each one of these things, the kernel and the image, as subspaces respectively of the domain and of the codomain. For the kernel, we just have to solve the homogeneous equation and find a basis for its solution set. That basis of the solution set for the homogeneous equation gives me a basis for the kernel of T. The dimension, the number of vectors in that basis, is going to be the same as the number of non-pivot columns in my matrix. In this example, that was 1. Meanwhile, for the image, we're asking which right-hand sides are going to give me a consistent system of equations. To find that out, we can just take those pivot columns out of the original matrix, because that is going to form a linearly independent spanning set for all of the vectors that we can get as the image of vectors under T. And therefore, the number of vectors in that basis, the dimension of the image, which is what we call the rank, is just equal to the number of pivot columns in my matrix. In this example, that was 2. And our basis was those 2 columns out of the original standard matrix. And this verifies for us in this example that if I add up the rank, which is the number of pivot columns, which is 2, the dimension of the image, plus the nullity, which is the dimension of the kernel, which is the number of non-pivot columns, that's 1, that I add those two things together, and the total is the dimension of the domain, which in this example was 3.